Swayam Prabha. Digital India. Educated India.
Good morning everybody and welcome to our course on Introduction to Mechanical Micromachining. In the last class we have seen about air bearing and we have found that these bearings are free from all types of wear as well as friction. So, that can be used for making a different type of sliding motion of the micromachining center. So, let us continue this topic further and let us understand what are the other components which can be a part of a micromechanical machining center, which can be used for getting a high precision motion and the very high accuracy. So, in the last class we have seen this comparison between the air bearing, hydrostatic bearing and the rolling bearing, and we have also seen that there are different advantages of all these three and disadvantages also. So, we have to find that which way we can get these particular things selected for a particular application, because everywhere you cannot use a air bearing and everywhere you cannot use a roller bearing. So, you have to find out a suitable application and then you find that how much is the accuracy and the precision you require, and maintenance is also one of the criteria. So, let us continue further. Now, coming to the linear drive. So, whatever we have learned till now, those were related to the bearing related issues. Now, suppose you want to move something linearly in one direction to another direction, and that is also similar to the air bearing, that you do not need any friction between these two. That means there should not be any contact. So, linear drive is one of the things which can be used for making a linear motion, that can be used in x direction, y direction as well as in the z direction. So, what are the differences between the conventional drive and the linear drive? So, mostly what happens if you consider the belt drive. Now, this is the belt drive, where what we do here, that we have a motor and on the motor there is a pulley, and on the pulley we put a belt drive. So, we can move, suppose this is the one component which we want to move, then you rotate this particular belt drive, and because of the rotation of this pulley in clockwise or anti-clockwise direction, you can transfer this component to another direction. So, what is that? That we have always a coupling of mechanical coupling, that means coupling of the payload to the motor through a mechanical transmission element. So, here what we are using? We are using a belt drive. Suppose this is the called, so it is called rack and pinion kind of thing. So, here suppose you are putting some component and then you give a motion of this motor, and then this rack and pinion will move and because of that you will get one linear motion of this part. Then there is a recirculating ball screw kind of thing. So, here also you can get this thing. So, what is common in all these three applications, that everywhere you are using a mechanical transmission element. That means, there is a physical contact between the belt and the pulley and the rack and the pinion and the gear and this particular nut. So, what is problem? That wherever we understood from that earlier, the roller element and hydrostatic bearing and the aerostatic bearing, that wherever there is a mechanical contact, we are end up with the friction and wear. So, if you want to avoid these things in linear motion also, then there is a option that is called linear drive. So, what is the linear drive? So, it is a direct coupling of the payload to the motor's moving part. So, this is the linear drive. So, what is happening here, that this particular top portion, it is levitated because of the magnetic field, and magnetic field will propel this particular movement. So, let us see this video, that how this thing will work in the actual condition. So, this is this thing we have seen in the last class, that we always need some frictionless thing. So, let us directly jump to the linear motor. So, what is the linear motor? So, now this is a conventional motor, correct, where we have a stator and one is the rotor. So, rotor rotates and stator is around the rotor, and because of this connection you are getting a circular motion or the rotational motion in the conventional motor. So, it is just something about these things. So, now what we are doing, that you just unwrap this particular stator. So, all the north pole magnets which are earlier in the circular part, now it is a flat surface, and the stator is actually lay down on the top of it, and this is the rotor which will take the form of this part. And now what is we are doing, that we are unwrapping the conventional motor stator, and then it is becoming a flat surface, and now this particular movement or where whatever you are putting on the top of that, it will move depending on the magnetic switch or the whatever way you are actually switching this pole, depending on that you will get the movement over this particular magnet. Now, you can see this is the magnet. So, this is the way linear motor works. So, in earlier case what we have seen that it was mostly a mechanical contact between the two surfaces, but here what is happening, that whatever speed you want to get this thing here, and the whatever way you want to make it more stiff, everything depends on the or which way you can switch over this particular power supply, so that you can get the movement in right to left or left to right direction. Right. So, these are the different components of the linear motor. So, this is called forcer. So, forcer is the things which will be put on to the top surface, and then forcer that coil will be wounded around this forcer, and this is the plate will be on which will be on the top of the forcer, and you put any component here. Suppose you want to move a workpiece, then put the workpiece here. If you want to move a tool, then put a mount this tool particular here, like that. And this is the stator, because we know that stators are required, so that you can put the magnets here, and because of that magnet you can get this particular motion of this forcer on the top of the stator. And we need a linear guides way, because we also want this is used for just movement, and after the movement then you have to also calculate that how much it is travel from one location to another location. So, this linear guides are very important, because the straightness and the linear motion, everything depends on the how much is the precision of this linear guides way. So, that is the thing. Then this is a position scale, because if you want to move with a 1 micron or 0.1 micron, then what you need an encoder. So, right now we are using here the linear encoder. We will see within a few slides after that what are these encoders, linear encoder, rotary encoders, but for this particular linear drive we are using a linear encoder, because they have some certain advantages over rotary encoder. So, this is the scale, then position encoder is available, then everything you assemble, and finally you are getting this particular thing done. So, this is the complete assembly. So, forcer includes, so this is called forcer, this part. So, it includes coil, because you have to create a electrical signal here. Iron core is there, because it is something like electromagnet kind of things, and thermal and protection devices, because you have to isolate this thing from the electrical problems. Correct. So, this is the stator. So, it includes magnet, base and the shield, because we have seen that we are unwrapping that conventional motor stator, and then it was becoming a flat surface. So, this thing is mounted below the surface. So, these are the magnets, and then we have to shield it also, so that there should not be any type of problem. So, these are the linear guides way. So, it is same function as the rotary motor has the right accuracy linear motor may employ air bearing instead of a linear guide way. So, here we have a different option, because in earlier lecture we have seen that we have a linear guides way, where we are using a different kind of bearing, hydrostatic bearing, air bearing. So, we can use air bearing here, so that you can even get a very extreme accuracy. So, even 0.1 micron or less than 0.1 micron motion is also possible, with a condition that you have a encoder also with a same resolution. So, these are the linear guide way, and this is the forcer plate on the top of that. So, it is base to fix the forcer, and after that you put something on the top. So, this is the position encoder. So, it is feedback to position the linear motor. So, here it will move along this motor, so that you can get the how much is the movement in the linear direction of this motor has performed. So, how this forcer moves? So, here, so this is the position 1. So, we have 3 coil here, and these two coils are energized, and we know that these are the magnets with a alternate pole arrangement. So, north pole, south pole, north pole, south pole, like this. So, this is the first position. Now, you can see that there is a switching over the between the two. So, now middle one is the off, and but this becomes the negative and positive depending on these polarities. So, now it has moved to second position, and now it is in the third position. Now, see, so it depends on how frequently you are changing this particular position of the poles. So, faster you change this particular thing, faster you can get the movement over the linear direction. So, this is the third position, this is the fourth position, again same thing will rotate. So, first two will energize, then first and the last one will energize, and then the middle one and the last one will energize, correct. So, this way you can get the linear movement. So, now if you increase that frequency change, then you can get the very high speed. So, this is the commutation, that is called how frequently you are changing this particular current direction. So, what are the parameters and definition we can think of? So, it is a continuous current. So, we have to apply the continuous current, so that you can get this particular movement possible. And we know that if you increase the current, what is going to happen, that we have a temperature rise also with I square R losses, and so we have to maintain that how much is the continuous current we can provide, so that your whole system will work within the desired or the limited temperature zone. Right. So, the second one is the continuous force, because now if you apply a force here, so how much is the force when you apply continuous current, how much is the force you can get when you are moving this particular platform. So, that is called forcer, and this is the encoder resolution, because everything depends on this encoder resolution. Even if you have very high precision motion of this linear motor, but you have not installed a sufficiently high resolution encoder, then what is going to happen, that you are not extracting the complete capability of this particular linear motors, that we have discussed I think few lectures back, that if your motor has a resolution of 0.1 micron, and if you install a encoder with a 1 micron, then whatever you are getting a motion, it is in a multiple of a 1 micron, not with a 0.1 micron. So, that is the problem. So, whatever things you get this thing. So, this is the encoder resolution, if it is a 1 micron and your motor has a 0.1 micron capacity or capability. So, this combination is not correct combination. What you have to do, you have to find out this one is also 0.1 micron or less, and then you get this particular thing here. So, this is the right combination, because whatever thing you are getting, at least you have to select a encoder in such a way that it has a much higher resolution than the system, then you can get the required thing done. Right. So, this is the position scale attached with this thing. So, there are different marking, that is called position scale, and each one you can get with a 0.1 micron. And then when you build this system, what you have to do, you have to supply the current also, you have to finalize that what is the straightness, what is the losses of the current when it is in under operation, heating of that particular system, all the things you can think by this particular analysis, that is called finite element analysis. You can also do the some frequency mode analysis, so that if it is under motion, then how much is the bending of this particular rail. If you are heating this particular thing, that means when you are supplying current, what is the heating of this whole component, where is the heat is concentrated or not. So, those things can be analyzed by this particular softwares. So, this is all the things about the magnetic circuit. So, let us not discuss this thing more right now, because these things are used for the simulation and analysis design purpose only. So, this is all about the linear motor. Right. So, this we have seen that this is our normal motor, with a stator and rotor is in between these two, it will rotate. So, if you flatten this particular stator and move this linear rotor on the top of that, you can get the linear drive. So, this is called the rotor text, it is called the secondary part, and this is called the primary part. So, that is the linear motor. And how it will work, that suppose this is called the Lorentz law. So, what is happening here, let me get this thing. So, this is the current you are applying. So, that is called the magnetic field. So, this is the magnetic field you are applying in this direction, that is in vertical direction, and if you supply a current in 90° to that thing, then it will generate a force which is perpendicular to both of these things. So, that is called Lorentz force. So, force F is generated when the current I and the flux density interact. So, along the length, so that is the length of this particular direction in which you are applying the current, whatever the component you are adding. So, this is the formula F equal to L into I into B. So, whichever way you want to give direction. So, suppose you want to get direction movement in this particular direction, then what you can do, that you change the direction of this current either in this direction or this direction. So, at that time this force will change. If you want to move this force here, then you have to change the current in this direction, current or the magnetic flux density. So, depending on this, whatever direction you are getting putting this magnetic flux density and current, you will get a force exactly perpendicular to both of those directions. So, we have to design this particular system in such a way that you get the motion in the required direction, not into the other direction. So, this is all the things is given here, magnetic assembly is given, that is attraction force, because magnets are located bottom, and we will see that some of these components are made of iron. So, iron will attract this particular thing, and then you can actually move in the different steps or the very high resolution. So, what are the different types? So, there are 3 different types of linear types. One is the iron core motor. So, what is this iron core motor? So, this is the particular forcer or the back iron, and these are the yellow color showing it is the coil, and these are the magnets located here. So, that is called winding, coil or winding, both the things. So, coil wound around the teeth of the lamination of the forcer. So, this is the forcer lamination, and then you put the epoxy and then wrap it and make it complete. Second one is called the ironless or the air core, because why it is called ironless? Because we are not using iron here. So, dual back iron separated by the forcer. So, this is the same thing, but this is the front view, this is the front view, and this one is the top view. So, we are looking from the top. We will see this thing more detail in the next few slides. So, what are the differences here? That now here the magnets have 2 rails. So, these are the magnets when you are looking from the top, and this winding is in the center, and on the top of that you are putting something. So, this is the something that these are the magnets, and this is the winding, and on the top of this part. So, we are looking from this direction. So, these are the magnets, and what are this thing? It is this small part, and on the top of that you put a plate, so that you can mount something from the top. So, this is about the ironless or the core iron, and coils held together with the epoxy, and another last one is the slotless. So, this is actually the getting advantage of iron core and the ironless part. So, it is all the things, it is in between these two. If you are getting some disadvantages of this, both the things will be here, as well as disadvantages of both the things also here. So, how this thing is there, that now some of the features are recreated here, because this is something which is similar to this ironless, but you are putting this particular rail also similar to the iron core. So, this is in between, that is called slotless, and coil and back iron are held together with the epoxy here in this particular case. So, let us discuss this each one with separate advantages and disadvantages. Right. So, first one is the iron core. So, this is the schematic diagram of that earlier things, whatever we have seen in the last part. So, this was the laminated forcer, this particular part, and this is the coil around the force lamination. So, these coils are wounded like this way, correct, and these are the rare earth magnets. This is the iron plate available, and these are some sensors are used for position sensing or current sensing, that is called Hall effect, and the thermal sensor. Thermal sensors we require because we know that by applying very high electrical current, then you may get the heating effect also. So, we have to reduce that heating effect for continuous and smooth motion. Right. So, copper winding around the force elimination over a single magnet rail. So, we have only one rail of the magnet. So, this is called rail magnet. So, what are the advantages here? Because here the highest force available per unit volume, because here what you will get a concentrated flux field. So, that is magnetic flux field is very concentrated. So, compared to all the three, right, compared to not other completely as different system, but here you will get more force. Efficient cooling, because windings are around the iron lamination. So, what is happening, that whole system is actually open. Now, you can see that this whole part, because this is moving in this direction or this direction, but this when it is moving, at that time you have a air circulation in all around the parts. So, that is the advantage, that here efficient cooling is there. So, temperature effect will be little bit less compared to the other two types. Lower cost, because it is simply the extension of this conventional motor. You just unwrap the stator and then use with a few sensors only. So, the cost is also less compared to other two categories. But what are the disadvantages here? Because here one disadvantage is the high attractive force between the iron forcer and the magnet track. So, what is that? Because this is the magnet, these are the series of magnets attached here, and our forcer which is made of iron. So, that is the big problem, right. So, if it is iron and this is very close to this particular magnet. So, what is happening here, that there is a high attractive force between these two, because we know that wherever you are putting magnet and there is some iron available nearby place, then it will be attracted by the magnet. So, same thing happens here also. So, because magnetic track will attracted by the iron forcer, and because of that there is one problem happens. So, that problem is called cogging. So, this is called the cogging. So, what is the cogging? That right now both things are situated here. Now, consider, so this is at the alignment position, right. So, now you have to switch over the supply, so that this is off position and this become the on position. So, this line and this line will be moved in this direction. So, when you are moving from one magnet to another magnet, what is happening here, that because we know that there is attractive force, and because of this attractive force you will get a velocity ripple, right. So, it is difficult to get a smooth motion from one magnet to the other magnet. You will get a very quick motion from shifting from one to here. That quick in the sense that it is extremely small, but when you are talking a motion with a micron of a or the less than 1 micron, this velocity ripple will create a problem at the micro scale. But if you see at the macro scale, when you are talking about the hundreds of micron, it may not make any difference at that location. So, iron force affects the thrust force as it passes over the each magnet. So, whenever it is shifting the position, it will get the velocity ripple. So, that is the problem of this particular type of motor. Second one is the ironless or the iron core. So, this is the same thing here, but now we have seen this cross section here. Now, you can see. So, this is the first thing. So, this particular thing is here, and these two are the red color part, whatever we are looking from this. So, these are the magnets, and on the top of that you are putting a forcer mounting plate. So, you put any object here or the tool here, then it will move with such a high precision. Now, difference between the first and two, that in earlier case we are using only single magnet rail, but now we are using two magnet rail. So, that is the another thing. You put the same Hall effect sensors, thermal sensor, everything in the coil, and then this is the more so back iron plate. So, that you can contain this all the things in a small volume, right. So, how this thing is different than under the force are constructed of wound coil held together with epoxy and running between the two rails, both the north and south in this particular case. So, it is moving in this in earlier case. What was the thing, that this whole thing was a from top to down and only single rail was there. So, that is the distinguished feature between the earlier case. What are the advantages here? Because now we are writing here ironless, so we are not using iron. So, once iron is absent, what is happened, that you will not get the cogging motion or the no attractive force between the two parts, right. low weight forcer, because no iron means high acceleration and the deceleration is possible here. So, this is the one motor which can be used for a very highly precise motion, where you need a very high acceleration and sudden deceleration, so that you will not get any type of motion error. So, that is very good motor for, but it has a low weight forcer. What are the disadvantages? The low force per package size, because it has a double rail design here, because here whatever the system you are using, it is very heavy. So, if you consider the package side, you will not get say the same amount of force here. So, here force is very less, but if you want to use with a very highly precise motion, or where you are not getting a force in a few microns of Newton, then this is the better choice compared to the other two motors. Low stiffness and limited load here, because what is happening here, that whole thing is mounted on the top of this part. This is the forcer and you are putting everything here, and this we know that everything is actually epoxy, and the other way we are putting with the epoxy. So, this is not actually the more stiff compared to the metallic joint. So, if you are putting more weight on the top of that, what is happening, that you have to sacrifice, or you have to compromise the stiffness of that. So, load whatever you are putting, it has limitation because of the stiffness of this particular motor. So, you cannot use a very heavy object on the top of that. Right. Poor heat dissipation, because in earlier case we have seen that we had a proper heat motion from one location to another location, but right now here what is happening, that the whole thing is actually moved or it is a very highly fixed within the system. So, movement of the air is very difficult here, and these are the motors which are located here. These are the magnets and this is the coil. So, if you want to dissipate heat from this particular part, then what you require, that you have to have air circulation through that, and once air is circulated, then it does not have the escape route also here from this part. So, for reaching to this particular location, it has to travel to such a large distance, and then only heat dissipation is possible. So, that is where the poor heat dissipation is there. Then the last one is the slotless wire. So, this is actually the mixture of the ironless and iron core. Whatever you are getting in earlier two cases, you will get both everything here. So, how this thing, the coil with a back iron contains within the aluminum housing over a single male magnet. So, here the one thing is that you are using a single rail. So, that is similar as the first case is, and then your winding is similar to the second case, that is called the ironless or the air core type of thing, and whole thing is actually fixed within the aluminum housing. So, you can actually secure for a later case, much better way to avoid some other problems. So, what are the advantages over the ironless? So, it is lower cost because we are using single magnet here, and earlier case the magnets were two, and it has a better heat dissipation compared to the first one only, not to the second one. Structurally stronger force are here available, because in first one cases that was not the case. More force per packet size, because the size is compact, but still you can get the advantages of the first one. So, that is the better way. Now, what are the advantages over iron cores? That is the first one. So, this ironless was the second one, whatever we have discussed, and advantage of iron core, that is first one, the lightweight and the lower inertia forces. Lighter weight means this lightweight is comparison with the first one, the iron core, not with this one, because this is the lightest compared to all the three cases. And we know that there is no cogging available, even though we are using iron plate here, but the distance between the forcer and the iron plate is large now. So, this is the completely you can avoid the course that cogging in the ironless kind of thing, but here you will get the cogging, but that cogging is very less compared to that particular first kind of thing. So, these are the advantages of this slotless with respect to ironless and the iron core. So, these are the different type of things. So, we will discuss about the advantages and disadvantages of this linear drive in the next class. Thank you very much.